Calculating the exact electromagnetic self-energy of a proton or neutron usually means navigating chaotic quantum math, but this actually shadows a rigid, perfectly symmetric geometry. The standard Baryon octet sits on a hexagonal grid. Sorted by charge, they cluster into exactly 3 classes. Mass corrections emerge. Class A gets 1 minus alpha over 10. Class B gets 1 plus 4 alpha over 45. Class C gets 1 minus alpha over 90. These aren't approximations derived from continuous field interactions. These fractional fine structure constants are strictly dictated by the mathematical topology of an icosahedral vertex. We have 8 physically distinct composite particles, varying wildly in mass and quark makeup, yet they all share exactly 3 geometric self-energy corrections. We need to look at the underlying mathematical architecture that forces this to happen. Within the framework of orthogonal discrete time-based topology, or ODTBT, particles occupy specific geometric lock positions inside an S12 phase space manifold. As a baryon locks into position, its internal structure couples to an icosahedral vertex, initiating the electromagnetic mass stressing. The hadron's net integer charge acts as a binary switch, determining exactly which of the 2 geometric pathway networks its energy will flow through. The precise magnitude of a particle's electromagnetic mass correction is not a continuous variable. It is a direct hard-coded output of this structural routing. Let's isolate a single icosahedral vertex to see these coupling channels function. Meeting at this center point are 10 directed edge half-arcs. These arcs form a coupling channel governed by the D5 symmetry group, structurally supporting both rotational cycling and mirrored reflective symmetry. To utilize this 10-channel pathway, a particle needs a directed current. Only charged baryons, with a net charge that isn't zero, possess the current necessary to flow along these specific edges. The alternative pathway consists of the 5 undirected geometric faces that intersect at that exact same central point. These faces form a channel governed by the C5 symmetry group. Unlike the edges, this pathway restricts current entirely to rotations. If a baryon is neutral, its directed currents inherently cancel out. Without a net directional flow, the particle's topological coupling is forced entirely through this undirected 5-face pathway. A baryon's base charge instantly dictates its topological denominator. If charged, the denominator is 10. If neutral, the denominator is exactly 5. This underlying geometry dictates how a baryon's internal constituents contribute to its mass. We define this interaction as proposition 2.1, the quark cancellation rule. Take the proton, containing 2 up quarks and 1 down quark. With a positive net charge, its current routes exclusively through the 10-arc channel. By Schur's lemma, the D5 channel distributes current equally, so all 3 quarks contribute via the sum of their squared charges. Look at the neutron on the right. With 1 up and 2 down quarks, it is neutrally charged, mapping onto the 5 undirected faces. C5 rotational symmetry forces the 2 down quarks to phase cancel, zeroing each other out, leaving only the single unpaired up quark. Because of this cancellation, neutral baryons apply only the squared charge of this single surviving quark to the 5-phase topology. Vertex symmetry acts as a strict mathematical filter. It strips a hadron's complex internal geometry down to a single topological coupling value. With these coupling rules established, the math naturally organizes the octet. We start with Class A, the charged baryons containing 2 up quarks, the proton and the sigma plus. This chart displays the exact calculation. For Class A, the sum of the square charges equals 1. We divide that by the 10 topological arcs, yielding the exact correction fraction of 1 minus alpha over 10. The negative sign dictates an attractive self-energy relative to the bare basin depth. The particle pulls itself tighter into the potential lock. Class C follows the identical D5 summing rule for charged baryons with 2 down-type quarks, sigma minus and sigma minus. The square charges sum to 1/3. Divided by the 10 arcs, the formula yields the octet's smallest correction, 1 minus alpha over 90. Class B encompasses every neutral baryon, neutron, lambda 0, and sigma 0. Applying the C5 cancellation rule, the single surviving up quark has a square charge of 4/9. Divided by the 5 undirected faces, it yields a repulsive correction of 1 plus 4 alpha over 45. But look closely at Class B. There is a glaring anomaly here regarding the lambda, sigma, and Z baryons. They all contain strange quarks. But because a strange quark and a down quark both carry identical -1/3 charges, they cancel exactly the same way under C5 symmetry. This creates strange quark transparency. They are electromagnetically indistinguishable at the vertex. Base charge geometry entirely overrides flavor profiling. That is the strict mechanical reason why wildly different particles, like the neutron and the doubly strange Z0, share the exact same self-energy multiplier. This three-class structure generates specific falsifiable predictions. We isolate the most critical one as proposition 5.1. By definition, baryons within the same class receive identically sized electromagnetic mass corrections. Therefore, the measured mass differences between them in physical experiments must originate elsewhere. That remaining mass difference is purely geometric, originating from distinct geometric seed lock positions in the S12 phase space. For prediction 1, identifying the sigma plus seed yields its exact mass ratio to the proton. The electromagnetic variables cancel out perfectly, requiring 0 fitting parameters. By rigidly isolating the electromagnetic contribution, the framework proves the existence of an underlying structural geometry that strictly dictates particle mass. We must also define the explicit boundary of this theorem. The general electromagnetic basin dressing rule requires hadronic confinement. Internal quark currents are strictly mechanically necessary. Without them, there is nothing to physically couple to the arcs and faces of the icosahedral vertex. Contrast this strict requirement against elementary leptons, like the electron, the muon, and the tau. They lack internal quark substructure entirely. Because leptons are point-like at accessible scales, they cannot distribute charge over icosahedral topology. Therefore, they experience exactly 0 basin dressing under this theorem. To address lepton mass, we have to employ completely different mathematical machinery, specifically the two-recursion spinor channel architecture of RCAM. The strict limits of this theorem precisely reflect physical reality. Topological structure dictates physical interaction, and elementary point particles simply operate in a separate structural regime.